And it's a pleasure for me to be here and be able to give you some thoughts about the Kondo effect. This I find a bit difficult because there was this beautiful colloquium also given by Professor Schneider, where I think he really focused more in the experimental aspects that I will do. I will try to focus more in the theory, and more than in the theory, in the interpretation of the Kondo effect. So my talk will have two parts, I would say. The first part is an introduction about what the Kondo effect is, where I will first emphasize spin flip, what the features of Kondo physics are, the role of transfer and how you can connect it to spin flips, and how you write this in Hamiltonians, and what can you learn from them. Once that this is done, I will move on to really the Kondo effect. How do you understand and what the physics is of the Kondo effect? This will take much of my talk, and then I will quite quickly go through three topics I picked up from my own research, which will be non-equilibrium Kondo, just to try to expand these ideas here in another direction, and vibrations, why vibrations can be important when you have the Kondo effect. And the last very brief point will be the orbital degrees of freedom that has created a lot of activity in the Kondo research. So the spin excitations for, I imagine, most of you that are working with the spin and doing inelastic electron tunneling spectroscopy and similar effects has an important effect when you're working on magnetic, atomic, and molecular adsorbates, because you can change the magnetic moment by flipping the spin of the electron that is being injected in the system. And this costs some energy, right? This is an inelastic effect. So this energy is due to the fact that your interactions are typically anisotropic, so you have to pay an energy to change the direction of your spin. Your spin is not anymore symmetric, spherical symmetric. It's not an SU2 spin anymore. Or that you have other interactions like exchange interactions between spins, right? This is a spin flip, meaning that the spin of the impurity will change in ±1 unit, right? That's the definition of a spin flip. Now, you can also have spin flips, but without paying energy. And that is actually the engine that moves the Kondo effect. Okay, so let me just very briefly give some historical and physical details about the Kondo effect. So the Kondo effect was discovered by studying bulk metals. And they came to the conclusion that these bulk metals contain magnetic impurities. So these are called dilute magnetic alloys because of these very tiny amounts of concentrations of impurities. And what they realized is that the behavior was strange, was different from what they expected of a normal metal, particularly with the temperature decreases. At very low temperatures, you find strange conductance behavior, strange properties with the magnetic moments, and strange thermodynamic properties. So the typical feature that everybody talks about when they're talking about the Kondo effect is the behavior in the conductance as you lower the temperature. And you have this graph here that represents what I'm trying to say. This is the resistance measured in, say, a big sample of gold. So this would be a bulk measurement of the conductance as a function of the temperature of the system, right? And in this paper from 1936, what they see, it's the Dutch group of Haas and Vandenberg, they see that the conductance starts decreasing, the resistance, this is the resistance, excuse me, the resistance, which is the inverse of the conductance, starts decreasing as you lower the temperature. This is exactly what you expect because you start reducing the sources of scattering. But then when you reach something like around 8 Kelvin, there is an upturn and the resistance starts increasing again. And it's sizable, you can see it. It's an important effect. It's not something that it is a problem, okay? And this is contrary to theory, because what you expect is that you reduce the number of scatters, the number of scattering events, say, and then the resistance should reduce and eventually go to zero. But there was also some strange magnetic behavior. And this is very soon they realized that they could control how the upturn of the resistance was increasing with the density of magnetic impurities that they were implanting in the samples. So then they realized that the magnetism was important, and they started studying magnetism. And one thing that you can easily, or more or less easily do, is to study the susceptibility, how the system is going to react when you apply an external magnetic field. And typically what this quantity is telling you is what is the induced magnetic moment when you apply an external magnetic field. The susceptibility has, on a metal, has two effects, the Curie and the Pauli terms. With one, the Curie term goes as 1 over the temperature, and it's telling you that you have some localized magnetic moments, and these magnetic moments are going to align with the external magnetic field. This is the term that you always have in localized magnetic moments. And then you will have the part coming from the itinerant electrons, the free electron gas, that is the Pauli susceptibility. If we remove this term, then we expect to find something like this as you go low in temperature. It's actually easier to represent 1 over the susceptibility. This is what this graph shows here. And then you would expect the red curve, something that as you approach 0, it goes to 0, right? However, instead, they found this curve here. This is the typical experimental data that you obtain. So what does it mean? So it means that if I write the same expression for the susceptibility in another way like this, that as you go to 0 fields, you can only have a finite magnetic moment. That's what you would expect following the Curie law, because you have always some impurities that are giving you a magnetic moment. If your susceptibility, this coefficient here, blows up, goes to infinite. That's exactly what you would expect in the red curve, right? Because in the red curve, you see this goes to 0, so 1 over t will go to infinite. And then it will tell you that you have a finite magnetic moment, even in the absence of magnetic field. But this is not the case. What this is telling you is that the magnetic moment is going to 0 when you go to 0, because this is a constant, right? So then when this is 0, since this is a constant, your magnetic moment will be 0. What it's telling you is that the magnetism gets screened in the Kondo effect. The magnetic moments disappear due to the Kondo effect. Another strange behavior was with the heat capacity. Okay, the heat capacity is like the amount of energy that you can inject in the system when you are changing the temperature, right? So if you look at the capacity is linear with temperature or low temperatures, and very soon people realize that in a free metal, 2 quantities, the susceptibility, which is the linear response to magnetic fields, and this prefactor, they are both proportional to the density of states. So then they expected that this would be a universal constant, which is called the Wilson or Sommerfeld ratio. Since they go to lower temperatures, they have the same behavior with the density of states. They expected that this would be 1. This is what it's called. It's always found. But now, if you have a dilute magnetic alloy, what you find is that this ratio is actually 2. And this is the hallmark of strong electronic correlations. This has created the field of materials that are strongly correlated whenever you have that this ratio behaves as this instead of this. Okay, so you also see that with temperature, the way you increase the amount of heat that you can deliver to one of these systems is also strange. It's also different from what you expect. So the first explanation about what was happening came by some work in the early 60s by Kondo, where he applied just perturbation theory and computed the conductance, assuming that you had spin flips. What I started saying. And this is the kind of graph that he could do, just taking the experimental points and fitting his calculations to the experimental points. And he could basically reproduce the behavior of the resistance as a function of temperature for different concentrations of iron impurities involved. So this was a very clear idea that he was really grasping the effect behind the Kondo effect. So actually, Kondo didn't discover the Kondo effect. What he did was to give the first explanation in terms of spin flip scattering. The idea is now that because you have an extra source of scattering, you're going to produce an enhanced resistance. Okay. Then people started studying the impurities and the electronic effects that that are behind this enhanced scattering. So there is a classification we usually do of the impurities depending on the electronic stature. So typically we say that depending on how the density of states, which is the number of states that you have per unit energy, with the character, this is P, projected density of states. So with the character of the adsorbate that you're looking at, or the impurity, right? You project on the wave functions of your impurity. So depending on whether this density of states is peaked at the Fermi energy, like in this case here, or below the Fermi energy as here, or very, very below the Fermi energy, you have three different regimes. One is called the mixed valence regime, like this one here. And the reason for that is because you have very big charge fluctuations that leads to, say, half and half populations of the charge state. So you will have N and N plus one charge states. So you have a mixed valence in your system. The valence of the system is changing, right? Because of the interaction with the substrate. In the Kondo regime, these interactions, these charge fluctuations are basically dead because you see that you are basically always occupied. Your populations go up to 90%, but you still have a little tail here that is going to allow you to empty and fill up your state. And then you are in the regime of the local magnetic moment where everything is really far away from the Fermi energy and nothing is fluctuating anymore. There are no fluctuations, everything is frozen, and you have a well-defined magnetic moment. So let me go into the Kondo regime and try to give an idea of why the charge fluctuations lead to spin fluctuations, okay? So this is a very simple scheme where I'm just plotting here the energy. All these states are filled up to the Fermi energy. And then you have an adsorbate level here, which will be our impurity, that is, say, occupied with one spin, okay? Now, because our density of states that I just plotted has this tail above the Fermi energy, it means that I have a certain probability that the electron can actually end up in a state that is inoccupied. So this can empty the state, okay? If I have, I will be in this regime here, right? Where I have like 90% of my level occupied, 90% of the time, and 10% of the time it will be empty. Okay, that's what this means. So then 10% of the time it will be like this. But then I can capture an electron and it will be most of the time, 90% of the time, it will be occupied. And then we have the same picture. This can go again, and then the spin can change because it doesn't have any memory of what the spin was before. There is no interaction that will try to keep the same spin in the system, right? So then what are we having? What we are having is that we have a spin that is 90% of the time in the place. Then 10% of the time it just goes away and then it comes back, right? And so what we are seeing is we cannot see when the system is empty because basically it's empty only 10% of the time. So we are looking at our spin and we are seeing that the spin is like this, and then suddenly it flips, and then suddenly it flips back, it flips in a random way. And that's the Kondo effect, right? In average, you will not have any spin on your system because you have spin up and spin down, flipping continuously. Okay, so what Kondo did was to take the well-known SD Hamiltonian at the time, and which is now called the Kondo Hamiltonian. And it looks like this. It's basically the operator for your impurity spin and an operator for the electron spin, the electron from the substrate, which is a spin density. That's why we put 0 here, because it will be different from 0 only when the electron is on top of the impurity. It's a local interaction, okay? And then let me just very briefly give you an idea of what kind of terms you're gonna get when you do this, when you use this kind of Hamiltonian. So for that, I need a basis set. And for the basis set, I need the something that describes my electron, a K number, see, because I'm in a metal, so I will have like plane waves that has a wave vector defined. And then the spin, in this case, I put spin up for the electron, fine? And then I will have my impurity of spin S and in a state SZ, it's pointing in some direction, fine? So this is already a state that represents my impurity plus 1 electron from the metal. So the Kondo Hamiltonian, then I can write it again like this, where I'm just taking my basis set and doing these projectors. You see, this is projecting above every state because I'm adding up everything. So this is actually the identity. I didn't do anything. This is exactly the same thing as this, because here I have the identity and here I have identity. I'm just projecting over everything. And then I realized that this projector has a part here, which is just my matrix element. Is the matrix element connecting one state with another state, okay? And then there is this new projector appearing, right? This projector appearing, I separate it in 2 parts. One is the spin from the impurity, and another one is the spin from the electron, okay? Now, this thing is not equal to this. Why is not equal to this? Because this, I'm assuming a single electron state. But here I do something more. I put operators that are antisymmetric. They anti-commute. So they take into account a many-body state. These guys are going to immediately create a metallic state for me, okay? So this is actually not equal. This is more than this, right? This is the many-body Hamiltonian. So imagine that now I want to look at spin flip. So spin flip, I put the spin, I look at the non-diagonal element here, spin down, spin up, and I just plug in what I told you, and I'm going to calculate this element here. So I separate the part coming from the impurity spin, okay? This I can do very easily because already Hamiltonian is prepared for that. And then I will have a part that has the spin of the electron and the orbital properties of the electron, right? I just separate the K. And then the K, the fact that I have to evaluate it only at R equals 0, I put in a Dirac delta function here that is different from 0 only if R is equals 0, right? This is just this element here. This element here will give me J over V, the volume, because the plane waves are normalized as 1 over square root of the volume. So it gives me this term here. And now this element here is going to, it will not give me any SZ component because it's non-diagonal. It has to be diagonal to give me an SZ component. So this will give me only SX and XY. So when I multiply, this is a dot product. So in this dot product, only the SX and SY are preserved. And you see that there is an I coming from the sigma Y and a 1 here coming from the sigma X. So this is exactly the element I get, which is telling me that if I have non-diagonal terms, spin flip terms, I'm only interacting with the transversal spin of my system. So this is just a spin flip, and I can actually see it in another way. Just write my full Kondo Hamiltonian like this, just the dot product, and I use ladder operators that allow me to go up or down in spin, depending on whether it's S plus or S minus. And I can rewrite this product just using the definition of the ladder operators, and I get exactly my spin flip term, where my spin from the electron goes up if the spin of the impurity goes down, or where the spin of the electron goes down if the spin of the impurity goes up. So it's a spin flip term. So we can also do this with a more complex Hamiltonian, the Anderson Hamiltonian. Anderson already realized that around the 50s that if you have something like a atomic Hamiltonian with a level, okay? This is epsilon A, the level. Now these operators here are just only destroying one electron in my level and creating it. So it's just counting how many electrons I have in this level. And then he just added a penalty function here that will cost energy to populate it twice. It's just, this is the Coulomb repulsion, right? This is the Coulomb repulsion of this level. So this somehow is a very simple model for an atom, really simplified model. Then a very simplified model for the metal. And you only allow for one more term, that is the hybridization between the two. You allow the atom to hybridize with the metal, okay? And this is exactly what this term is telling you. You destroy one electron from the metal and you create it in the atom. So these terms will be the hopping terms that can transfer one electron from the metal into the atom. And this is just the Hermitian conjugate. Your Hamiltonian has to be Hermitian conjugate, right? This is just a complex number, okay? So in this kind of Hamiltonian, the levels are not spin polarized. Huh? This level is not spin polarized, but this automatically will create a spin polarization because it's going to make the put a penalty to double occupations, right? So you will not have spin up, spin down in the same level. So you can go from the Anderson Hamiltonian to the Kondo Hamiltonian when you are in the Kondo regime. And that is what the Schrieffer-Wolff transformation does. You can show that in this regime where you basically have 90% of your level populated, then these are equivalent if you define an exchange interaction J in your Kondo Hamiltonian that is basically the hybridization square divided by the difference in energy of the levels. Okay, just simply V squared divided by energy will give you an anti-ferro. You see there is a minus here, so this is an anti-ferro interaction. So the spins want to be, the electron spin that comes from the metal wants to be anti-aligned with the spin from the impurity. Well, there is something missing, and it is that, of course, there are charges around, so you need to include the charges. And the Anderson Hamiltonian includes that. So the Kondo Hamiltonian doesn't include it. You have to add it. You have to add a potential scattering term if you want to map the Anderson Hamiltonian into the Kondo Hamiltonian through the Schrieffer-Wolff transformation. Let me simplify a bit and assume that we have a more or less wide band, so we can just take our density of states and just only evaluate it at the Fermi energy. And in that case, I can define a broadening. This is basically the Fermi-Golden rule because it's V squared times the density of states. So this is the interaction between the atom and the metal square and the density of states. And this gives you the broadening. It means how the levels are going to be broadened because you are interacting with the metal. The inverse of this will be a T1 time. It's how long your electron stays in the atom before it goes into the metal if there's an empty state in front of the metal, right? So instead of V squared that I wrote before, I write gamma. You see that now my couplings will be just gamma here. And now I have to divide by the density of states because it was V squared, remember, and the epsilon A. Well, in the limit U infinite, so I kill one of the terms that I had before. U infinite means that I will only look at singly occupied states, okay? I don't look at double occupied states. So let me show you a very simplified model for the Kondo problem. Anyone knows how we are doing time-wise? Good. So a very simplified model. The idea is to try to grasp most of Kondo physics with just 2 electrons. Now, the model is the following. For the metal, I take 1 electron that you see I drew a very long line here. Why? Because I am going to allow double occupation. So this one will have U equals 0. I can have doubly occupied states. But for this one, that is the short one, it's a short line, this is my adsorbate or my impurity. That is a localized electron state. This is at the localized electron state. That's why U is equal to 0, because electrons don't see each other. But this one, they see each other very strongly. So I will use U infinite, okay? I don't allow double occupancy. So the good thing about that is that my Hilbert space get reduced. You see, I have 2 electrons in my system now, huh? So the number of electrons are well defined. No voodoo physics here. And now I have these possibilities that are one possibility here. This is a singlet, okay? Singlet, I cannot have a triplet because I have a non-magnetic metal, okay? I have a singlet. And now I can have 1 electron in this level and 1 electron in this level. So this would be epsilon m plus epsilon a, and this will be 2 epsilon m in energy. Fine? And here, how many states I have? I have 4 states. Why? Because I have spin down, spin up, spin up, spin up, you follow me, right? And I can write it also in the basis set of the spin, of the total spin, and then I will have a singlet and a triplet. That's 4 states, right? Okay, now I'm going to add an interaction between this and this states. Why? Because this is a metal, this is my adsorbate, and they hybridize. This chemical hybridization term that I was talking about, the one that is included in the Anderson model. So if I add this hybridization term, well, before I add it, it's equal 0, so I get exactly this kind of a spectrum, right? Epsilon A plus epsilon m, this will be 4 times the generator, and 2 epsilon m, that is a singlet, so it's only 1 state. I add the interaction, and because the interaction doesn't change the spin, it's just a hybridization, so it allows 1 electron to go from one to the other and come back, so the spin doesn't flip in this process. Then I will connect only states with the same spin, and they will produce like a bonding anti-bonding splitting. This is exactly what you see here. And how much the split is basically v squared over delta, the change of energy of the states here, this difference in energy. This is what the Schrieffer-Wolff transformation tells you is the exchange interaction. And you see that it's exactly what you would expect because it's splitting your triplet from the singlet. And that is exactly J, right? So the first thing that you see in this model, this very simplified model, is that if you do a many-body calculation that takes into account the full configuration, this is only 2 electrons, it's easy, we can do it by hand, then your ground state will be a singlet, despite the fact that you are adding 1 adsorbate that wants to be magnetic, okay? This is the same as in the Kondo effect, your ground state is a singlet. And that the first excitations in the system, the low energy scale, are given by magnetic excitations. You go from the singlet to the triplet. And here, the triplet, you see, you have 3 states. So on top of that, you're going to have lots of magnetic excitations. You are going to have a peak very near the Fermi energy because you need very little energy and you have many possible magnetic excitations, okay? Now, this model, what it's telling you is that the metal is not magnetic. If I allow a magnetic metal, like if I allow this guy to have the triplet here, this wouldn't work, okay? It's this trick that makes this thing work. So I can do a better calculation, same idea, but now instead of using a single state, I can use, say, a Fermi C, and the Fermi C will be this state here, okay? This is a many-body state that is just filling up all states up to the Fermi energy, okay? So now I mix 2 types of configuration. The one where with the absorbate or the impurity is empty, and the one where the impurity has 1 state. And I keep the number of electron constant, so I create a hole here, okay, when I do that. And I just mix them up, and I solve this Hamiltonian. This starts being a little bit more difficult, but I can do it variationally, okay, I can minimize. So the first thing that we find is that, yeah, we recover that the ground state is a singlet. And then we get that the first excitation energy that before was just J, this is more complex because now we have many more magnetic excitations. And they are distributed with this, the gap, so to say, it's not strictly speaking a gap, but say the first excitation energy is something that is exponential with the distance of the level, epsilon A, divided by gamma. This is the inverse of your J that we were talking about before, okay? And this is the bandwidth of your metal. You decide your metal goes from one energy to another energy. It's just all the possible metallic states here, okay? So you see that this gives you an exponentially small scale. You have an exponential here, and this is minus. So as soon as your level starts being far away from the Fermi energy, this is going to die very quickly. you will not have more excitation like this. So this excitation energy actually is how well your ground state is stabilized, right? Because it's the energy you have to pay to destroy your ground state, to go into the excitations, right? So I could have called this the ground state energy. Now, if you look at the coefficient of the Fermi seed, the first coefficient that I showed you before, this coefficient here, what we obtain if we do this very simplified calculation is that it's basically 1 minus the occupation of your adsorbate, of your impurity. So what does it mean? It means that if the occupation of the impurity is 1, this is 0. It's telling you that you have no contribution from your Fermi seed in this calculation. Okay, so you cannot have the Kondo effect. If Na is equals 0, then this guy is 1. Same idea. You have everything in the Fermi sphere now, and the Fermi state and Fermi sea, excuse me, and then you don't have any Kondo. So you need something that is in between, right? More things. People what typically do is instead of talking about the ground state energy or the excitation energy, they talk about the Kondo temperature. Okay, so it's just translating this quantity in a temperature scale. So it's just the Boltzmann constant that is in between. So the Kondo temperature is actually how well your ground state is stabilized. So what do you need to get Kondo? You need degenerate ground states because you need spin flips. So here the degenerate ground states will be spin up and spin down if we have spin one system. But eventually you can have something more complex like spin one, where you have these spin flips between SZ equals -1, SZ equals 0, SZ equals 1, right? You can have all these spin flips here, and you can perfectly have a Kondo effect. And remember that the level that is hybridizing with the metal has to be almost filled, but not completely filled. In the moment you fill it completely, you freeze it, and you don't have any more Kondo physics, right? So let me show you again the density of states, but now using a many-body calculation that takes into account everything I've said. So you get this kind of graph here. So this is, again, your density of states. This is the energy with respect to the Fermi energy of your different states. And you recover your, say, 1 electron density of states representing the level of your impurity in front of the continuum of states of the metal. And this represents the charge fluctuations because we saw that all these ones are empty and these are occupied, right? So if it's 90%, means 90% of the time is occupied, 10% is empty. And then you see that there is this large peak appearing at the Fermi energy, and these are spin excitations. These are magnetic excitations of your system. You have many of them in a very small energy scale because it's basically what you need to destroy the Kondo ground state, okay? Now, if I zoom in, you realize that, so this is a zoom of the peak. You realize it's a little bit asymmetric because it's really, this would be the Kondo temperature, the energy you have to give the system to destroy your ground state, okay? So it has to be totally positive here. Why is it totally positive? Because I'm doing a U infinite model here. So I only allow single occupancies. If I allow double occupancies that you find a U, then I will get the same one because I can as negative, and then I will get something symmetric around the Fermi energy, okay? So this is, the asymmetry comes from the fact that I'm using U infinite and I only allow electron processes. I don't allow whole processes, okay? So now let me show you some results that, from experiments and calculations. So here, these were cobalt on copper and done with the DSTM. So you approach the STM, the tip approaches, and what the DJ did was to measure at different distances and different conductances. So in the tunneling regime, when the tip is far from the adsorbate, what we find is what we always expected, is that in tunneling, you will have a simple case where basically you're reading the density of states of your substrate. So the density of states of your substrate and the conductance, this is the result of the calculation, they match. The difference is that in the conductance, this axis is the bias, and this, in this case, is the electron energy. Here, if you look carefully, you will see that you have many curves for each different bias used in this calculation here. Okay, you see, there is like some sort of broadening here. It comes from the fact that these are many different biases, okay, calculated. But you see that they are just proportional, density of states and conductance. This is what you expect in tunneling. But now when you move in the contact regime, something different happens. Because now in the contact regime, your couplings to the electrodes, which are the hybridizations we were talking about, the hybridizations are basically the same between impurities and the two electrodes, right? So if we assume it's the same, then what we are going to get is, of course, larger currents because we're in contact, but particularly we are going to get a symmetry in bias, when the bias is positive and negative, because basically it's the same thing to go from left to right in electrons going from one electrode to the other, or going from the left electrode to the right electrode in the other one. Is this a message? Oh, okay, yeah. Fine. What happens when you are in this contact regime? Well, that the conductance is not the projected density of states anymore. And you see it here, this is the projected density of states, or I call it here transmission. And the first thing that you realize is that depending on the biases are different calculations for different biases. There are now two peaks appearing instead of only one peak. And the reason is because you have two Fermi levels since you are applying a bias. And each Fermi level is going to give you a Kondo effect. So you get this kind of behavior, split peak. And then you realize that actually the broadening increases very much as you start increasing the bias. You are producing decoherence. So this is the bias-induced decoherence of the Kondo effect that appears very clearly in the projected density of states. Now you take each of these biases, you integrate them to produce a current, and you make the differential conductance, you derivate the current, and you get this result here. A beautiful Kondo peak, totally symmetric, no features, nothing. You lost all the information when you look at the conductance. And this is a very interesting result, I think. Particularly here, what they did in the experiment was to use what many people do is to use different functions, particularly this one is the Frota function, that gives you an idea of what the Kondo temperature is. And you see that when you compare to the non-equilibrium calculations, they match very, very well. So it seems that the experimental way of working, it makes totally sense. Now, vibrations are interesting. Why? Well, because it gives you more information and it tells you also that you can couple vibrations and electrons. The idea is that when the electron goes through your system, you can excite the vibration. You give energy to the vibration, so your electron will end up at the end of the Fermi energy where you have an enhanced density of the states, as we saw because of all these spin excitations that are around there in the Kondo effect. So then you expect to enhance the vibrational excitation, but you also expect to have more damping of vibrations. You expect to broaden the peaks of the vibrations. So this is what we saw in this case here. These are experiments done on cobalt-C molecules that are these molecules here. They have a C5H5 ring up and down, and in between they have a cobalt atom. So this is a spin 1/2 system, and they show Kondo effect. They also show this kind of constant current steam images. So if the molecule is isolated, basically all the electron structure adds up and makes something completely symmetric. So you see these donuts that appear here. Now, if you put the molecule on a step edge or on the tip of the STM, then you very quickly develop this kind of asymmetries that come from the nodal plane of the molecular orbitals at the frontier molecular orbitals. So you can look at the differential conductance and actually at the derivative of the conductance, the second derivative of the current. And you will discover lots of peaks. And these peaks distributes with this energy that more or less match the DFT calculations for the vibrations. We went a step further and we introduced that in our code with vibrations, and we can reproduce fairly well the experimental data. This is when the cobalt-C molecule is on the tip, so it's lowly coordinated, like in a step edge. But if you put it on a terrace, you realize that the system, this is the experiment, the system, all these peaks get much broader, and you can match them also reproducing with the same kind of calculations here, just by increasing the coupling to the substrate. You reproduce this kind of behavior. The interesting here there are several messages. One is that indeed the peaks are broader. Well, this is the theory, right? But the peaks are broader, so we think this comes from the Kondo effect. Also, you can see them clearly that it would be very difficult to see on a substrate, on a metallic substrate, because you have the enhanced density of states from the Kondo thing. And when you increase the coupling, you can actually see a lot of features that one would eventually think that they come from some localized states, and they are not. They are just coming from the vibrational Kondo effect. And let me finish my talk, if it's still okay, with the last part of this Kondo colloquium, where I would like to talk about the orbital degrees of freedom. And this is what we call the isospin flip, because the idea is that you have the spin, but the orbital moment could also be a spin, right? So it works similarly. This is work done in collaboration with Matthias Bode. And the experiments were done on manganese phthalocyanines on this surface. Is actually a silver crystal with antimony on top, and that creates a special pattern. And the geometry was interesting because it leads to certain distortions on the molecules. So here, what I want to say is that if you have orbital degrees of freedom, say you have two orbitals, so now you can have one populated or the other populated, and that will be our isospin degree of freedom. You could have up and down. But at the same time, you have the SU2 symmetry coming from the spin. So now you have SU2 from the spin, but this one can also give you an SU2 symmetry. So in total, it's something like an SU4 symmetry, which is a really, really high symmetry. You have an extremely highly symmetric system that will give you an extremely robust Kondo effect, because you have a strong symmetry that you have to break. Now, if you have something that lifts the degeneracy of these two levels, like for example, a Young-Teller effect that distorts the molecule and lifts the electronic degeneracy, then you will reduce your symmetry. You will go to a lower symmetry like Z2 here. And but you still can see this through inelastic effects, because now you can pay this energy and see the effect of having Kondo plus an inelastic effect coming from the orbital degrees of freedom. So this is what exactly we did here. And let me just show you a cartoon instead of showing you the boring experimental results. Excuse me, maybe Matthias is listening to this. And so here you have, if you are at negative bias and you are below the energy you have to pay to match this energy difference, then you can open this channel where you start feeling this empty orbital. Manganese phthalocyanine looks like this. Instead of having one single electron, as I showed, it has a one single hole, okay, in the frontier orbitals. And you have this kind of channel. If you change the polarity, then what you can do is start filling up your hole with the tip, and then you have this other channel. So you will see these two guys. But now, if you look carefully, you see that this one is happening when the tip is on top of ligand 2, and this one is happening when the tip is on top of ligand 1. So you're going to have a spatial resolution. You're going to be able to match where your orbital is by looking at the differential conductance. And this is exactly what the experimental, I show the experimental data here, shows. So this is the bias, this is the differential conductance, and you see this. If I had plotted everything with the same color, you would see just the typical steps that appear when you have an inelastic effect. But here, depending on whether you measure in one ligand or in the other ligand, you're going to see one step or the other step, as I just told you. Okay? And these are the wonderful calculations that are much more interesting, but I think I will talk about it another day. And we have really good agreement with the experiment. So maybe I just wrap up by saying that spin flips are leading to strong electronic correlations. Not intuitive. Generally, this is complicated physics. And the phenomena that they produce in electron transport is really interesting. Thank you very much.
Thank you very much, Nico. We have time for questions. We have about 15 minutes. because we are also broadcasting this on Zoom, we have to use the microphone when we are here in the room. So please wait for the microphone to ask. And for people who join us on Zoom, you can either put your questions in the chat and I will read it, or you can raise your hand and we'll try to patch you in if Zoom allows. There we are a little bit depending on the technology. So let's take questions from the audience in the room first. Who has a question for Nico?
So I just have one question. I want to understand something. You said that if it's around the Fermi energy, exactly at the Fermi energy, it's what you call charge fluctuation. And charge fluctuation induces Kondo effect, if I understand what, spin flip excitations, right?
I explained it wrongly.
Okay, or I understand wrongly.
No, you're correct. In the way I said it, you're totally correct. In order to have the Kondo effect, what you want is that the charge fluctuations don't wash out the spin fluctuations. So you need to reduce the charge fluctuations, but you cannot kill them, right? You have to leave them somewhere where they're still important, so you have spin fluctuations. So it's this idea that if you want to have Kondo, you need to have a spin. And then when you're looking at this spin, 90% of the time it's there, right? And then 10% of the time leaves. But you don't see this leaving because it's too short, right? So the only thing that you see is that from time to time it flips, okay? And that is the Kondo regime. So you need, like, say, something around 90% or a bit bigger, okay? If you go to the mixed valence regime, that is the one that you are describing when your peak is in the middle, is at the Fermi energy, then the charge fluctuations are so strong that you don't see this flipping. What you see is that this guy goes and then after some time comes back, and then after some time comes back. So it's a much lower process and it doesn't give rise to the spin fluctuations. So that is not the Kondo regime. You don't see Kondo there. You could say that you have like a Kondo peak, but it's actually the mixed valence peak already. It's just your density of states that are the Fermi energy, and it's extremely broad. You don't have a well-defined Kondo temperature.
Okay, so why in the calculation you show that what you call the Kondo peak is around the Fermi energy, like in the PDOS, slide 30?
All right. So here.
Exactly.
The charge fluctuation peak is this one, right? So this one would be the one that was trying to be represented here, right? So it would be this one, right? This would be the charge fluctuation peak. And you see here, this is a 1 electron calculation, so I don't have a Kondo peak. So then when I add the many-body effects, then I open this channel, the possibility of having spin excitations. And they show, because there is a new peak that appears at the Fermi energy, this one. This is a new peak that is telling me that I have a Kondo effect. And this is the one that you can easily see in STM, because it will be a zero bias anomaly, or almost zero bias, because the Kondo temperature is very small typically, right? So depending on whether you're in a U infinite or almost U infinite regime or not, then you will see this peak a little bit outside or just center of the Fermi energy.
So it's just excitation in the degenerate ground state from S = 0 to S = 1.
Well, that would be in the very simple model I wrote. But in a more realistic case, it will not be a single triplet. It will be much more complicated, right?
Yeah. Okay. Thank you.
Okay, I see there is a question on Zoom, or Shinje pushed the wrong button. If you have a question, please, Shinje, unmute yourself and go ahead.
Yeah, I have few questions, and thank you for a very nice talk at first. And before going to the Jantella effect, in that slide, I have several questions. Could you go to? Yeah, exactly. No, before.
In this slide, you have a question?
Before this image, before this
one?
slide. Yeah, here.
Oh.
Yeah, I hope my question is not too rude, but as I understood, the Kondo peak is usually at the Fermi level, but in this experiment, the Kondo peak is not really at the zero bias voltage at figure D and E.
This one here, you see, this is fairly good at the zero energy, right? Because this is the derivative. So if you derive of a peak, it will give you something that is up and down, right?
Yeah, I mean, at
So
figure
then this is really a zero energy. This is really a zero energy, yeah. So you see, this is the theory. You see, the theory is giving you something very close to zero also. And when I make the derivative in the theory, I get basically the same thing. Huh?
Sorry, Nico, I think she is talking about the green one, D and E. Did I understand correctly? Yes.
You're talking about this one.
Yeah, exactly.
Okay, this one is the same story as here. The difference is that now this is much broader because the couplings are much stronger. So the Kondo temperature increased a lot. And we are in a almost U infinite regime. So then it's very asymmetric. And this is what you see here in the experiment. You see this is very broad and asymmetric. And on top of that, you have all the vibrations. And the vibrations are creating all this strange behavior here. You see, we have lots in the, I think the theory is more clear. You have lots of peaks here, okay, coming from vibrations, but also on this side. And because you are in an almost U infinite case, this tail is much longer than this one here. That's the asymmetry coming from the U infinite.
Yeah, okay, then if I am allowed to ask this again, and usually I saw people are verifying that it's Kondo effect, Kondo peak by using the extra magnetic field. But I mean, how can you be sure that it's Kondo peak or something from other?
You're totally right. I guess that it's always very difficult to know really if your zero bias anomaly is really Kondo effect or something else, right? Here, the best thing that we have is that you have a very consistent picture between the different degrees of coupling, depending how you coupled your molecule to the substrate. Like this is weakly coupled, this is strongly coupled. And I mean, and this is the difficult part here. And what you're saying, that is this really Kondo? Well, in the theory, we only have Kondo. That's the only thing that we know. And okay, you can say, well, yeah, but this doesn't match perfectly this. Well, yeah, okay, right. But look at the vibrations, right? They don't really match either. So I don't think that it is the Kondo difference, the problem here. I think the theory pretty much proves that this is really a Kondo peak.
Okay, thank
again,
you.
You have to trust the theory.
Yeah, and my last question is, sorry. Yeah, my last question is, you said it is coupling with the vibration mode, right?
Say that again.
So you consider the vibration mode of the molecule and the Kondo effect.
Right, yes.
Do you think it's also possible for the single atom? I mean, much smaller mass.
I guess, I mean, you have many less modes, right? So, and the electron vibration coupling can be smaller for an atom. A molecule, you can have a very large electron vibration couplings, right? Yeah, but yes, it's possible, yes. Okay,
then maybe the coupling will be lower if it is.
Probably, yeah.
Okay, thank you.
Okay.
Thank you very much. We have one question in the chat that is connected to this, I guess, that in some molecules, they have low energy wobbling modes. And is there any indication of strong coupling between such modes and spin fluctuations?
I don't know. I don't know. Whenever I try to do very low frequency modes, like, looking into this region, it looks very difficult to do theoretically. That's like everything I can say. I guess there are many, but it's difficult to see. Here, it really gets into the broadening, so you can confuse it with the Kondo temperature. Now, whether a low energy mode has a larger electron phonon coupling, I think that is not straightforward. I don't know.
Okay. Any additional questions? None from the audience. So we do have time for one or two more from Zoom. If there are any, please do raise your hands. You can either speak on the chat or directly to us via video. Thanks, Shinje, for testing this. It seems to be working really well. Okay, if there are no further questions, sorry, smiley on the chat. If there are no further questions, then let's all thank our speaker again for today's talk. Thank you very much, Nico. And on that note, I would like to remind everyone that there will be, another colloquium that is scheduled with Philip Kim. The date, I believe, is not exactly set yet. So please check our website or sign up on our website so you get the information. And yeah, thanks everyone who's here with us, and thank you all on Zoom. We'll see you in the next colloquium.